This is a demonstration of the Power Concepts home energy storage system. We have a demonstration system here with an inverter in this area, batteries below, and over here we have simulation of house circuits. We have distribution board next to the grid interface, which communicates back to the inverter. We have various loads that we can turn on and off, and this variac can simulate different amounts of current coming in from a PV array. Over here we have a laptop which allows us to control and monitor everything that goes on in the system. This is the inverter. This particular prototype was built for a marine application, so it's a 24 volt inverter, and it was built for a 20 kilowatt system. So we have 4 of these 5 kilowatt modules can be mounted side by side on this capacitor board here. For the grid tie application, we're only using one 5 kilowatt module. Up here we have the control circuits. Here is a FPGA which controls the high frequency switching of the power devices, and over here a processor which handles the higher level control and communications. In here there is a low voltage board with a transformer on it, which steps up the 24 volts to a 500 volt bus, and here we have a high voltage board which pulse width modulates the 500 volts to produce a 230 volt sine wave. Down here is the output filter, which removes the pulse width modulation frequency and leaves the 50 Hz sine wave. The actual power module looks like this. This is the low voltage board, all surface mount components, so it's very easy to manufacture and very small. There is a transformer here which steps up from the 24 volts to 500 volts. That is quite small, and it can easily handle 5 kilowatts. This is the high voltage board, again all done with surface mount and mounted on its own heatsink. In this section here we have a rectifier which turns the output of the transformer into the 500 volt DC, and in this section the pulse width modulation. These two boards mount with the heat sinks tip to tip to make a nice channel to blow air down for cooling. This is the connection from the inverter to the grid interface. For demonstration purposes we have a flexible cable with a plug-in connection, but in a real installation this would be fixed wiring in the house. Here we have the communications link from the grid interface to the inverter, done with low-cost plastic fibre optic cable with a simple screw connector. The cable can be cut with a sharp knife. There are no special installation tools required, and it can be run along with the mains cable between the inverter and the grid interface. There is no chance of electrical interference. If we turn on the grid interface, you'll see the red light coming along the cable, which is the data coming from the grid interface back to the inverter. This is a good way of working out which cable is which. We know that that's the transmitter from the grid interface, so we plug it into the receiver on the inverter. This is the grid interface, which is the part of the system that makes it very easy to install. So all the current monitoring for current going in and out of the house is done close to the distribution board for the house. You don't have to take thick wires from here to the inverter and back again. Inside here we're running the main connection from the grid through a Rogowski coil to sense the current and back out to the distribution board. And also in here we're measuring grid voltage, and we have a phase lock loop which synchronizes up to the grid and then communicates the phase information to synchronize the inverter with the grid. Down here we have various circuits which would normally be in a house. We have a non-essential load circuit which is directly connected to the grid. This one's not backed up when the house goes to standalone mode. We have essential load circuit which is directly powered by the inverter whenever the house is being run standalone from the inverter and not connected to the grid. We have a circuit standing in for the electric hot water heater, and also in here we have a relay that can turn that on and off. So if you're running standalone, that would normally be only turned on when the batteries were fully charged. This we're not demonstrating today, but we can plug a micro inverter in there and have a simple connection to a small solar array. And here again is the variac that controls some currents in here to make it look like there is a solar array feeding current into the house. This is the battery for the demonstration system. Not exactly the same as we'd put into a real installation, but using much the same technology. Inside each of these blue modules there are 32 cylindrical cells. They're 26 650 cells, and that gives us 3.3 volts at 100 amp hours. These are lithium iron phosphate cells, and we have two modules connected in parallel to give us 200 amp hours, and then 8 of those sets in series to give a 26 volt battery. This gives us a usable capacity of around 5 kilowatt hours, which is suitable for demonstration purposes, and in fact would be quite suitable for running a small home system as well. This is our control and monitoring program for the system. We have here a system overview. You can see the various currents and powers being measured in the system. This is a development tool, so we want a nice fast response so we can see things happening. So these figures haven't been filtered very much and they jump around a little bit. So here we have a grid connection coming in, and we have the grid voltage currently 228 volts and the frequency 49.99 Hertz, and also the current coming into the house. Here we have the solar array, and that currently is putting 1.6 kilowatts into the house. We have the electric hot water cylinder on, which is consuming 700 watts, and the remainder of the power coming in the solar is going through the inverter into the battery. So we have 24 amps charging the battery. Up in this region we have some control sections, things for setting the real and reactive current coming into the house. Over here we have more detailed information about the grid interface and the inverter, and down here we have information on the battery. We have the voltage of all 8 cells, we have the current going into or out of the battery, and also the voltage of the highest voltage cell and the voltage of the lowest voltage cell, which are used to restrict the charge and discharge current when the battery is fully charged or fully discharged.